Jai Hind all. So, previous lecture we have discussed about operation of BJT and basic structure. We have left the discussion on the structure of actual transistor. So, today we are going to discuss about the operation in more details, the other modes of operation. So, in previous lecture we have discussed about the operation of BJT in active mode, when emitter base junction is set to forward biased and base and collector region, means base and collector junction is made reverse biased. So, we have discussed about the active mode of operation, in which we can use the MOSFET as an amplifier. Now, the another mode of operation of BJT is saturation mode. Saturation mode is obtained when both the junctions made forward biased. So, now today we are going to discuss about saturation mode operation. Consider bipolar junction transistor. This is the BJT. This is NPN BJT. NPN. It's a emitter. It's a collector, and it's a base. So, we are willing to have BJT in saturation mode. In active mode, this junction is made forward biased by connecting battery in this function, and this is the value of VBE. If we have applied some AC component, then the total voltage will be VBE. So, electrons will be emitted, means this junction will be forward biased only when VBE should be greater than the knee voltage. If VBE is greater than, if VBE is greater than or equal to 0.5 volt, then only emitter base junction will be forward biased. Otherwise, it will not be on, it will not conduct. So, first thing is we should have VB greater than or equal to 0.5 volt, so that this transistor will be in active mode. The second thing is that if we want to, this terminal, that is CB terminal, in forward bias, in reverse bias, then base, then this collector should be connected to negative positive terminal, and base is connected with negative terminal. If the value of this base to collector voltage will be smaller than VB by 0.1 to 0.3 volt, that is VBE, means now in saturation mode the terminal of battery is reversed, means negative is connected to N, positive is connected to base. So, this terminal will be forward bias if and only if VBC will be smaller than VBE, then this will be forward bias, otherwise it is in reverse bias condition. So, for the saturation mode operation, VCE, that is voltage between collector to emitter, will be 0.3 volt at least. If the value of saturation voltage, that is value of VC, if we are considering it with respect to emitter, then if the value of VCE will be equal to 0.2 volt, then this will be in saturation mode. So, this is VCB. So, VCB, this is the condition for VB. For the saturation mode, VC should be equal to VBE minus VC. So, this is the condition of saturation mode operation of BJT. So, this is the diagram. In we have seen that in common base configuration in active mode, IC will be proportional to VBE by VT. In fact, IC totally depends on VBE in active mode. In active mode, there will be no variation in the value of IC with VCB. So this is the plot between IC and VC. So if we have taken IC at the vertical axis and VCB on the horizontal axis, then in active mode operation there will be no variation. Variation in current is found only with varying VB. If VB is constant, then IC will not be varied. So this is the active mode operation characteristics. And in saturation mode, as we lower down the value of VCB, in fact, when the value of VCB reaches 0.3 volt. So if VCB will be less than or equal to 0.4 volt, if VCB less than or equal to 0.5 volt, saturation mode reached. So in this region we are having negative VCB. If the value of VCB will be less than 0.4 volt or equal to 0.4 volt, the BJT enters in the saturation mode. So it's a saturation mode operation characteristic curve, where if we increase VCB in negative, that is negative, with increasing negative VCB, the current at the collector terminal decreases. So these are the characteristics of collector current with respect to VCB when NPN transistor is working in the saturation mode, and emitter current will be constant. So if emitter current is constant, and means VB is constant, and we are varying collector to base voltage which is less than 0 volt, then BJT enters in saturation mode and we are getting curve like this, means collector current will be decreasing with increase in negative VCB. For active mode of operation, the collector current doesn't depend upon VCB. So now we are going to discuss about the some more details of BJT. Before detailing, now this is the symbolic representation of NPN and NPNP, because this diagram is not very suitable when we are using BJT in circuits, in complex circuits. So in complex circuits we are using symbols. So this is the symbol of NPN transistor, this is the symbol of PNP transistor, collector, base and emitter. This arrow shows the direction of current. So in this direction the flow of electrons will be from N to P. So the direction of emitter current will be from P to N, from base to emitter. This is the direction of current, that is base to emitter. So in the symbolic representation we are getting the direction of current from base to emitter in NPN, and in PNP emitter to base. So this is the symbolic representation for NPN and PNP transistors. This shows the circuit diagram for CB configuration. This is for CB, means common base configuration, means base is common between emitter and collector. So this is VBE, and this is you can get, just a minute. So in active mode, emitter to base junction is forward biased by applying VB in this fashion, and collector to base junction is reverse biased by applying battery in this function. The positive terminal of battery is connected at the collector terminal, negative terminal of the battery is connected to the base. This is VCB. So the same is drawn here with the symbolic representation of BJT. So this is VCB. This is for NPN, this is for PNP. It is NPN and it is for PNP. This is the common base configuration, and transistor is working in the active mode of operation. So this is the circuitry, and in active mode of operation, if we discuss about IC VBE curve, then IC depends upon VBE, and if we write the equation, IC is equal to e to the power VBE by VT into IS. In fact, this is the exponential equation. So the collector current varies exponentially with increasing VBE after a certain voltage, that is 0.5 volt in the case of silicon BJT, and this value of voltage can be varied if we increase the temperature, and the value of this IC greatly depend upon the temperature. If we increase temperature, then this increment in current will be obtained early. So if it is worth 0.5 volt, after that we are getting rapid increment in the collector current with the increasing VBE. Then with increasing temperature, this VBE means this cutoff or knee voltage will be lowered to 0.2 volt or much more. So as in silicon diode, the voltage across the emitter base junction decreases by about 2 millivolt for each rise of 1 degree centigrade in temperature. So voltage will be increased as we are getting increment in IC, exponential increment in IC at the lower value of VB if we increase the temperature. Now we have ideally we have only considered collector current is just because of emitted electrons. Ideally we have considered the value of IC is only because of number of electrons injected from the emitter terminal. We have ignored other factors, but in actual practice, as in the case of PN junction diode, there will be some thermal generation of carriers, because this junction, I again redraw the circuit diagram. Just a minute. In NPN transistor, this is N, this is P, this is N. This is the NPN transistor. This junction is forward biased. This is base and this is emitter. And this junction is, this is base and this is emitter. And this junction is reverse biased by connecting this N terminal to the negative terminal of the battery. Reverse bias. If we are increasing reverse bias at this PN junction diode by increasing reverse bias voltage, that is VCB, by increasing reverse bias voltage, the depletion width will be increases. The effect of VCB. Ideally, we have ignored the effect of increasing VC. We said that the collector current IC doesn't depend upon the value of VCB. We said that the value of IC that is flowing through this terminal, this IC doesn't depend upon VCB. And we have considered only the effect of majority carriers. But if it is a reverse bias condition, then a space charge region exists between this PN junction diode, and eventually electric field is obtained. Because of the effect of this electric field, a drift of minority carriers take place. Means minority carriers on N side means holes on the N side and electrons on the P side will also drift through the junction. Because of this drift phenomena, we are getting some saturation current. So if we write the current equation of the collector current, IC is equal to IS e to the power VB upon VT. From this equation, if IS is constant, either if the value of IS is very less, then IC depends only on VB. But if IS changes, then the value of IC will also be affected. So, in common emitter configuration, generally in common emitter configuration, which is shown in the diagram, in common emitter configuration, if we set VB constant, and only varying VC, VB is set constant and we are varying VC. Now, also I am writing the equation IC is equal to IS e to the power VB by VT. In this equation, VB is, now I am putting VB as constant. There is no variation in the value of VB, and we are just only varying VC. What about the effect of variation of VC? Now see at the diagram. This is NPN transistor, NPN. Note that this base region is lightly doped. This is base, this is emitter, and this is collector. This base region is lightly doped, okay, and this junction, if we are getting common emitter configuration, then this junction, that is collector base junction, made reverse biased. Okay, this is the value of VCB. This junction made reverse biased and this junction made forward biased, but it is constant now. We are just only considering the variation of VCB and the value of IC. If VB is made constant, it is VB. If VB is made constant, there will be no variation in the value of injected currents from N to P, and there will be no variation in collector current because of VB. What should be the effect? Collector current should be constant. But in this situation, if we are varying VC, ideally collector current doesn't depend upon VC. But now see the effect. This is VC, common emitter configuration. Just a minute. It's a common emitter configuration. This is common emitter configuration. So we write the voltage VCE. So now we are increasing VC. Okay, what the effect of increasing VC? This is reverse bias PN junction diode, and this is the depletion width. You can write L, and the actual width of and the effective width of this depletion region will be the WB, written as this. If L is increased, if VC is increased, then this diffusion length will be increased more. With increasing diffusion length, WB will be shortened. Now this is WB minus L. With increasing VCE, there will be increment in the width of depletion region. Means with increment in VCE, we are getting depletion region is more wider. What is the effect of in widening depletion region? The effective width of base region will be lowered. Means base width is narrowing. With the effect of increasing VCE, modulation in the width of VB base region is called as base width modulation or base width narrowing or early effect, because the scientist J.M. Early have described this effect firstly. So with the name of J.M. Early, it is called as early effect. What would be the effect on characteristics? width will be increased, means space charge region will be increased, and with the increasing space charge region, the electric field, which is due to the availability of immobile ions in this region, will be increased. If the electric field is increased, then the drift phenomena will be more frequent and IS will be increased. So, with increasing VCE, base width region is more narrow, means width of the base decreases. What the effect? IS will increase. With increasing VCE, IS increases. If IS increases, maybe the value of IS is very less. If IS increases, IC will also increase. So, because of base width narrowing, instead of flat characteristic curve, we are having some slight increment in the value of IC with increasing VCE. This effect is known as early effect or base width narrowing or base width modulation. So, this is the effect of increment of VCE and this effect is dominant in common emitter configuration. This is common emitter configuration, means emitter is common between collector and base. This is the common emitter configuration, CE configuration. So, in CE configuration, the early effect is dominant, and this is the ICVCE curve for the early effect. Because from this diagram, from this diagram we are getting only the description of characteristic curve. With this diagram, we are actually getting what happening with the increasing VCE. So, I can draw this diagram fresh, very clear to you all. I am redrawing it. Okay. Now, I am redrawing the structure. This is NPN transistor, EBJ, emitter base collector. This is NPN. This is N, it's a P and it's a N. Forward voltage is applied between these two. This is VB if AC is also applied, and this terminal emitter is common, is made reverse bias VCP. Okay. So, with increasing VCB, this depletion region will be increases. With increasing this depletion region, this width decreases, WB minus L, as we are increasing depletion width L. So, total width WB will be decreased to WB minus L. So, this is the early effect. It is very interesting to study it, and all the topics can be studied from these books. So, from my side, it is my recommendation to study these books, Benji's Statement and Sanjay Banerjee, Solid State Devices. It's a Pearson publication book, and DNE Man, Semiconductor Physics and Basic Semiconductor Physics and Devices, McGraw-Hill's publication, and a few diagrams have been taken from and concepts are also taken from Cedra Espin Microelectronic Circuits, Oxford University Press, 2015. So, thank you from my side.